For our first lecture, we're going to more formally define what a circuit is than what you may have seen in your Engineering 120 courses. So we're going to define a circuit as an interconnection of electrical components I misspelled electrical. That contains at least one path that current may flow through. So this is our definition for a circuit. So I'm going to draw an example of a circuit that is going to contain only general circuit elements. So for instance, we may have something that looks like this. We have some element A connected to some element B connected to some element C, connected to some element D, and finally we might have a fifth element, element E, like so. So this is a generic circuit because we don't know what type of circuit elements A through E are. So they could be resistors, capacitors, inductors, diodes, batteries, transistors, memristors. The options are not limitless, but pretty close. So we have an interconnection of generic circuit elements. One thing that I'd like to point out is that all of these circuit elements are what we would call a two-terminal circuit element. So each element has two branches that we can form connections with. That's why it's a two-terminal element. The points of interconnection between the circuit elements are what are called nodes. And what I like to do to identify nodes is I start at one circuit element and then follow along the connection to the next circuit element and then circle back. So this whole connection between element A and element B represents one node. Okay, so the node is the point of interconnection. We're also going to have a node here, which I have drawn in purple. So this is a point of interconnection between elements B, C, D, and E. And we also have a third node at the bottom that's going to connect elements A, C, D, and E. So just to reiterate, the points of interconnection between the circuit elements are referred to as nodes. All right. Now, this particular circuit has, I believe, 6 loops, where a loop is defined as any closed path that current could take. So for instance, I'll draw all of the loops in red. So this would be considered one loop, from element A into B through C, and then closing back in on element A. So current could circulate around this closed path, So that's one loop. This closed path through element C back down through D, circulating like so. We have another closed path here through element D, circulating around through element E. So those are 3 loops. We also have a loop around the exterior of the circuit, so current could flow through A, B, E, and then return to A. Or we could have, so that makes 4, and then our 5th and 6th paths, or loops, I'm not going to draw, I'll just follow them with my finger because this is going to get a little too messy. But we could have a loop that effectively contains this loop and this loop together. So we could go from A through B, down through D and return, or we could go through C, down through E and return. Those are our other 2 loops. So there are 6 total loops. And so again, a loop is simply any closed path that current could possibly flow through. And we'll revisit this concept of loops an awful lot when we get to mesh analysis in about a week and a half. So let's circle back around to the concept of nodes. In my opinion, nodes are a very, very important characteristic of circuits because they help us to identify the types of connections that we see between our electrical components. And there are 2 basic types that we will deal with. Series connected, where in a series connection, there is a single point of interconnection between 2 circuit elements with no branching paths. And so what I mean by that is if we look at this node between element A and element B, this is a single point and there's no other way for current to flow away through from this node, right? So if current is flowing up through element A, it has to flow through element B next. It can't split off and flow in any other direction, so there's no branching paths. So that means because there's only this single point of interconnection, elements A and B are electrically connected in series. Our other option is a parallel connection. And in a parallel connection, what happens is the nodes at each terminal of a device or an element are shared. So for instance, elements C, D, and E all share this top node in purple, and they all share this bottom node in orange. So that means that elements C, D, and E are electrically connected in parallel. So they all share purple and they all share orange. B is not in parallel with C, D, and E because while it does share purple, it does not share orange. And A isn't in parallel with C, D, and E because it does share orange, but it doesn't share purple. So these are the 2 types of characterized connections. Now, something that a lot of students tend to struggle with at the beginning of a circuits course is that there really is a third option, and that third option is neither series nor parallel. So if we look how element B and C are connected to each other, or B and D, or B and E, effectively B with anything other than A, it's not a series connection, because while there is a point of interconnection, there is a branching path, but it's not a parallel connection for the reason I stated earlier. They share purple, but they don't share orange. So B is not in series or in parallel with elements C, D, and E. And one thing that students don't seem to get early on is that that's perfectly okay. Not everything is going to fit into a nice and neat little box. And we're going to learn analysis techniques and combination techniques to get around the fact that we don't have a perfect series connection all the time or a perfect parallel connection all the time. All right. So I think that's enough of going over the jargon. So now we're going to talk about the different quantities that we're going to be dealing with as we perform circuit analysis. And the first one that I'm going to talk about is voltage. So in your engineering 120 series, you've probably dealt with the concept of voltage on multiple occasions. If you've ever changed a battery in a remote, you've actually dealt with voltage or plugged in an electrical item. But in the 120 series, you didn't pay an awful lot of attention to what's called the polarity of a voltage, and that's going to be extraordinarily important in this circuit analysis class. So you may have seen something like element A had a drop of 5 volts, where element A was a resistor or something like that. In this class, this is an insufficient definition, okay? All voltages are going to be defined not only by a magnitude, but also by a polarity. So I'm going to arbitrarily assign a plus sign to this top terminal and a minus sign to this bottom terminal. And what these polarity means is that there is a 5-volt difference between the electric potential energy here, where the positive polarity terminal is, and here, where the negative polarity terminal is. So if you go pick up a AA battery, you'll notice that there's a plus sign on one end and a minus sign on the other. A AA battery is a 1.5 volt voltage source. So that means there is a 1.5 volt difference in electric potential between the top terminal of the battery and the bottom terminal of the battery. And so that's going to lead us to actually our first definition for voltage. Voltage can be defined as a difference in electric potential between 2 points in a circuit. Mathematically, we could develop an expression for this definition where V, the voltage, between points A and B in a circuit, so let's say this is point A, it's a node that has a fixed electric potential, and this is point B, another node that has a fixed electric potential. The voltage would be defined as the line integral from A to B of the electric field dotted into a differential line element. Now this definition comes from electromagnetic field theory. This is an offshoot of Coulombs Law. And we're not going to use it a whole heck of a lot in this class because it's really beyond the scope of what we're going to be doing here. But I think it does actually show pretty clearly that it's a difference in potential between 2 points because it's based on a line integral from one point in the circuit to another point in the circuit. For those of you that have had Physics 201, which at this point I hope is all of you, we could say that the work done moving some charge from one point in a circuit to another point in the circuit is given by the charge multiplied by E dotted into dl, where this expression QE is simply the electrostatic force, okay? So this is force multiplied by distance, which is work from a physics perspective. So if we look at the difference between these two expressions, we can come up with another relationship or another definition, right? So these two expressions are identical, except that this guy is 1 over Q times this guy. So another way to express voltage is the work or energy per unit charge needed to move charge around the circuit. Particularly in this case from point A to point B. And this definition here, I like it because it relates voltage to our next topic of interest, which is current, okay? Voltage is what's providing the push that causes current to flow, right? Hopefully you remember from your engineering 121 class that current is simply when charge moves in one particular direction. It's actually the time rate of charge. We'll get into that in a second. But what's providing the push that gets the current to go in one particular direction is the voltage. And I think this definition adequately sums that up. So let's circle back around to the concept of polarity real quick, okay? So I have decided that this 5 volts, there's a 5 volt drop over element A, positive polarity on top, negative polarity on bottom. That is the exact same thing as a voltage drop of negative 5 volts, but with the opposite polarity. So this and this represents the exact same information, okay? So probably your first maybe a couple of weeks of this class, it may be in your best interest anytime you deal with a negative voltage to convert it into a positive voltage by changing the polarity. May make things a little bit easier on you. Before we move on to current, I want to talk about how voltages are represented in circuits. So our basic voltage drops is fairly well defined, right? We have a magnitude and a polarity. Voltage sources, however, can come in a variety of different schematic representations. So our first representation is the one that you're probably the most familiar with. All right. This is the circuit schematic diagram for a simple battery, where it is assumed that the long bar is the positive polarity terminal and the short bar is the negative polarity terminal, and it will typically have some magnitude assigned with it, and I'm going to call this VDC because batteries supply DC or non-time varying voltages. This is what you saw overwhelmingly in your engineering 120 courses. In this class, we're going to represent DC voltages usually by this symbol. A circle with a plus sign and a minus sign, where the plus sign represents the positive polarity terminal, the minus sign represents the negative polarity terminal, and we'll still have some magnitude, which in this case we'll call VDC again. So this is our symbol for a generic DC voltage source. So not specifically a battery, maybe a power supply or something like that in the lab. This is a generic symbol for that. And later on in the course, we will deal with AC voltage signals. And so those will be supplied by AC voltage sources. So it's the same circle with a plus and a minus representing the positive and negative polarities, but it will also have a little squiggle in it that's representing that the signal is changing with time. Traditionally, this is associated with only sinusoidal signals, but in this class we'll be dealing with exponentially varying signals and piecewise functions and stuff like that. Anytime it's not constant, I'm going to use this guy. Positive polarity terminals for the plus sign, negative polarity terminals for the minus sign, and we would see that this is some AC voltage that varies with time, where AC, I'm meaning it just time varying. So these are our three types of what are called independent voltage sources, okay? And an independent voltage source means that the voltage drop over the terminals of the source is independent of any other quantity in the circuit. So that means that if, let's say, I had a 5-volt battery, this battery is supplying 5 volts regardless of what is connected to the battery itself. So it doesn't matter if there's a resistor, capacitor, inductor, whatever circuit it's connected to, it is supplying 5 volts. And the amount of current that flows through it is not related in any way, shape, or form to the voltage drop over the source. So that's what it means to be an independent source. There are also dependent sources. And there's going to be 2 dependent voltage sources that we'll deal with. Dependent sources are given by diamond symbols, and dependent voltage sources specifically are diamonds with a plus sign and a minus sign, okay? Our first dependent voltage source is what's going to be called a voltage-controlled voltage source. Okay, VCVS stands for voltage controlled voltage source. And so there's going to be some factor K multiplied by some controlling voltage Vx in the circuit. So just for the sake of argument right now, let's change element D into a voltage controlled voltage source. And I'm going to say that the factor K in this case has a value of 3. And I'm going to define the voltage Vx to be the voltage drop over element B, positive polarity on the right, negative polarity on the left. So what this dependent voltage-controlled voltage source does is it says, well, whatever value Vx happens to have, the potential difference between these 2 points is 3 times that, okay? So this voltage Vx controls the terminal voltage we see across our voltage-controlled voltage source. So K should have units of volts per volt because the controlling variable is voltage, and the output is also voltage. Our other option is a current-controlled voltage source. So it's going to have the exact same symbol, which makes it a little bit confusing. But instead, we're going to see that there's going to be some quantity G multiplied by some current. So the terminal voltage of this source is dependent on some constant quantity multiplied by a current. So if we made this guy a current-controlled voltage source, let's say this is Ix. then whatever current is flowing through element B from direction left to right gets multiplied by a factor of 3 volts per amp to make the units work, and that's the voltage that appears over the terminals of our current controlled voltage source. So current controlled voltage source. G is what's known as the transconductance, and it has units of, sorry, not transconductance, transresistance. I'm getting myself mixed up here. This should be actually R. Volts per amp. So current goes in, is multiplied by a quantity that is expressed in volts per amp. You get volts at the output. So I apologize for that simple mistake there. All right, so these are the 5 different types of voltage sources that we'll see in our circuits. This guy is specifically a DC voltage source. This guy is specifically an AC voltage source. Our dependent sources can be either AC or DC. You usually won't see a squiggle even if it is an AC quantity. It's going to take students a bit to get used to these dependent voltage sources, but I promise if you just think about what's going on instead of being intimidated by them, it's actually pretty easy to utilize them inside your circuits and figure out what's going on using circuit analysis techniques. All right, let's move along to current now. All right, so I already have a current drawn on the board, so let's just, instead of having it labeled as IX, let's call it 3 amperes, okay? Where the ampere is the unit of current, and I fully define this current because it has both a magnitude of 3 amps and a direction flowing from left to right. I think you probably had to pay attention to directions of current and things like that in your Engineering 120 series, maybe more so than you did voltage polarities, but we are not going to fully define a current unless we have both a magnitude and a direction. Current is defined as the time rate of change of charge passing a point in a circuit. Mathematically, I of t is equal to the time derivative of the charge q with respect to time. So it's the change in charge divided by the change in time, which is exactly what you used in your Engineering 120 courses. From this, we can actually rearrange, and this is not a definition for current, so I want to be clear about that. We can define charge in terms of current. This is often useful. So it's going to be the integral from some time when we know what the charge is to some later point in time of the current with respect to time, where tau, I'm using it as a dummy variable representing time because I shouldn't have t here. If I have t in my limits of integration, it just gets confusing. So tau in this case is just a dummy variable that represents time, plus some known charge at time t naught. And I want to be very clear that in this expression, this term q of t naught is not included in the integration. So charge is effectively current multiplied by time plus some initial amount of charge that we could observe. And we'll use these mathematical relationships a lot in our example problems and things like that. Now, we saw that if we had a negative voltage, we can convert it to a positive voltage by changing the polarity and vice versa. And we can do the exact same thing for a current. So if this 3 amps direction left to right is the same as negative 3 amps direction right to left. So if you ever get a negative value for your current or ever see a negative value for a current, you can simply change it to a positive value by changing the direction of the current. All right, let's see. The next quantity that I want to talk about is power. We are going to use what's called the passive sign convention in this class. So let's say that I have a generic element. Like so. I'm going to define a voltage drop over this element, V, and I'm going to define a current flowing through the element, like so, I. Power is simply the product of V times I. Okay, that's nothing particularly difficult, and it's the exact same relationship that you used in your Engineering 120 courses. But what we're going to be paying attention to is whether or not the element is absorbing power or supplying power, okay? So this current I, as I have drawn it, is flowing into the positive polarity terminal of the element based on where the positive polarity of the voltage is. So when the current is flowing into the positive polarity terminal, we consider this element to be absorbing power. And the amount of power that it is absorbing, P, is equal to I times V. This is regardless of whether or not this current has a positive or negative magnitude or this voltage has a positive or negative magnitude, okay? So, for instance, if this were 3 amps, and this were 5 volts, then this particular element would be absorbing 3 times 5, 15 watts of power. However, if the voltage were negative 5 volts, then this particular element would be absorbing negative 15 watts of power, okay? The negative sign implies that it's doing the opposite of absorbing, which we'll call supplying. So instead, I may have cases where I have a generic element. Here's V, and here's I. So the current is flowing into the negative polarity terminal first and then out the positive polarity terminal. In this case, the element is considered to be supplying positive power or absorbing negative power. And the amount of power supplied is, again, P is equal to I times V. Now, I'm not going to lie, this probably seems extraordinarily confusing to you, and it's going to continue to feel that way until you get a significant amount of practice with it. In the web work assignments, it may not be obvious what you're being asked for. The reason I say that is because some problems will say which of the elements are supplying power or which of the elements are absorbing power, and they don't really clarify what they mean by that because it just depends on how you're looking at it. All of the elements are supplying power, just some of them are supplying negative power, or all of the elements are absorbing power, just some of them are absorbing negative power. So whenever you see any problem like that in the web work, what it really means is which of the elements are supplying positive power or absorbing positive power, so that there's some way to differentiate between the two. And we'll get lots and lots of practice with that. On your exams and stuff like that, I'm going to give you problems where I ask you to tell me, how much power is absorbed by element A or how much power is supplied by element C. And I'm going to, the first thing I'm going to do on those problems is I'm going to put in boldface absorbed or supplied so that you know very specifically. I'm not trying to trick you or anything. I just want to make sure you can perform the calculation. But another thing is that I'm going to put both the positive answer and the negative answer so that you have to be able to evaluate and properly apply this passive sign convention. So when we get to the in-class portion of this lecture on Monday afternoon, we will work a few example problems where hopefully this will be presented a bit more clearly. Alrighty, so power by definition is current times voltage. We consider an element to be absorbing power if current is flowing into the positive polarity terminal, and we consider an element to be supplying power if current is flowing out of the positive polarity terminal or into the negative polarity terminal. I'm trying to decide whether or not I want to talk about Teligens's theorem. Teligens's theorem, I'll just mention it briefly. So Teligens's theorem is effectively just the law of conservation of energy, but it's really more of the law of conservation of power. All it says is that the total sum of the power absorbed in a circuit must be zero if you're calculating everything as absorbed, or the total power supplied by a circuit must be equal to zero if you're calculating everything as supplied. So what it's really saying is power, and therefore energy, cannot be created or destroyed in a circuit. It has to be conserved. And we'll use that to our advantage in analyzing a few problems on Monday. All right, so the last topic that I want to talk about then is energy. So energy is just the total power absorbed or supplied, which depends on which one we're looking for, over a fixed period of time. So mathematically, energy is the integral from some point in time t1 to some point in time t2 of the power with respect to time, which is the exact definition you would see in physics class or something like that. So power and energy are related. Energy is the integral of power, so we could say then, circling back around to power, power is the time rate of change of energy. And mathematically, power would be the derivative of energy with respect to time. So these two are just the same equation, slightly manipulated. All right, let's see. So we've talked about what a basic circuit is. Nodes, loops, series connection, parallel connection. And we've talked about the four quantities that we'll be asked to deal with in our circuit analysis problems. Voltage, current, power, and energy. When I talk to you guys on Monday afternoon, if anything here didn't make sense, please use the first few minutes of class to ask as many questions as you can think of to help me and your classmates better articulate this material to you guys. All right, so I'll see you guys on Monday afternoon.